Yeah, KG, we can start. We'll be ready to join.
I'm ready. Shall I share my screen?
Yeah, KG, yeah.
Okay, right. So everyone is seeing my screen. So today it is there are four topics: QML and classical versus machine learning, then real world use cases, then we have feature scope and opportunities. So QML PPT remaining things are Q&A, meaning that question and answer. I will take a notes, the later share with you, such that you will have a reference to this one. Cool. So let me start with a high-level introduction to QML. There is a lot of content are there. I'm not going to spend time there. Straight away, I'm starting with this one because I know that we have Q&A session. During the Q&A session, I will cover from this PPT whatever necessary. Uh, QML, somewhat it is considered the next big thing. Indeed, there is a blog post titled QML, the next big thing. If you search in the internet, uh, I will I will show here. Hope you are seeing my screen, right? QML, the next big thing. You will see one post. This Geeks for Geeks, this post,
Yeah, it's
and then
visible.
there
Yeah.
is, yeah, it is very interesting post, and I recommended there's a quantum Z gist. That is the one thing what I, and then this is my post what I created for Conference 42 uh, 2 years back, and this is very interesting to see. Yeah, this is what I was referring, the Quantum Insider post. Yeah, this is one thing. Yeah, by Anisha Mushti. This is the thing what I am referring, and we will see a lot of good um, content from this post. So I strongly encourage you to visit this URL. So now in continuation, 1 minute, what happened? Oh, still in the. So it is the intersection of machine learning, quantum computing, optimization techniques, and for those coming from classical machine learning, already they know the intersection of data science, AI, ML, DL, RNN, or RL, all those things as a Venn diagram. I prefer Venn diagram when we discuss the top or high level conceptual, because that will give you a clear understanding what are the skill set you should possess before jumping into quantum machine learning. If you are good at machine learning and optimization technique, your it is the intersection of intelligent algorithm, then optimization. But the intersection of three things are QML. So what is QML, and is it replacement for any classical machine learning? To be honest, it is not the case. Not all machine learning models can be utilized or can be um, use the quantum computing capabilities. The main reason why it is not so easy, you have to remember one important architecture of quantum computer and classical computers. Classical computers are based on Turing machine, which is built on persistent storage as one of the component, meaning that the finite state automata is using a persistent storage. That is what the Turing machine. But in case of quantum Turing machine, there is no persistent storage. Only the even it is not finite state automata, but it is a Turing machine, which is depending on no persistent storage architecture. So only processing power. So because of this capabilities or this limitation of persistent storage or unavailability of persistent storage, not all classical machine learning can be moved to quantum machine learning. That is the one important thing you have to understand. So in that case, you may be interested. Okay, if that is the case, what are the other possible machine learning model? So there are, I know, quantum support vector machine, quantum neural network, quantum transfer learning, and quantum GAN, and quantum LSTM, then quantum physics informed neural network, and quantum federated learning, quantum reservoir computing. Yeah, to my knowledge, these are the machine learning model explored. But classical, we have many other models. Okay, for your reference, I recommend you to go to this Penny Lane website, pennylane.ai. Here, if you go to this explore demos under machine learning category, you will see there are many um, example or demonstrations of machine learning model, quantum machine learning models using Penny Lane framework. So this one will give you a clear picture from where you can start understanding existing quantum machine learning capabilities in the industry. Okay. Now, in continuation to this our discussion, why we need QML, quantum machine learning, as the um, model. One thing is speed, next one is accuracy, third one is security, fourth one is scalability, and novel application innovation. And if I demonstrate a quantum support vector machine, see, in the interest of time, I'm not going to demonstrate that one, because that one needs installation of IBM Qiskit, and at the current state of IBM Qiskit, it is very challenging because Qiskit is upgraded to 2.0, but the quantum machine learning still depending on Qiskit 1.4 or 1.1. So because of this version conflict, I cannot demonstrate QSVM now, but I can share my experience of last execution. Last execution I executed in. Okay, I can. I think I can share my screen also for the execution. That came. The classical system ran on few seconds. I'm referring to Iris dataset. Hmm? Let me. Here itself I will put. Okay, after this one. Hope you are seeing my screen. QSVM observation. So classical executed 5 seconds and accuracy 96 percentage. Quantum SVM executed 38 second 8 seconds and accuracy 60 sorry 70 74 point some percentage. This is what you will observe if you run a quantum support vector machine. Now I am claiming these are the benefits. Obviously you will understand what is the meaning if this is the performance, real performance, what you are observing, and but what you are claiming, they are not matching. The only answer is that one of the answer, but the important answer is that we are still in the nascent stage of quantum computing. We have only 1121 qubit from IBM, and IBM has promised IBM Starling, which is going to be released in November, that may give better performance, but we are not sure. And Pennyline is promising some good performance, but that is also depending on real hardware, right? So the QML domain is eagerly waiting for powerful, error corrected quantum computers. Since that is not matured, these benefits we are not able to acquire this, or we are not able to get these benefits. Is that answer the question for all of your? Uh, that might be running in your mind. Why KG is claiming that these are all the benefits, but in reality, this is what he observed. Then what is the meaning? And this is the answer. Okay. And please feel free to add questions now. I will start answering your questions starting from 5:25 or 5:30. Then, what are the challenges as I discussed now? And this is the comparison of QML and classical machine learning. This one I want to spend some time because the CC is the classical machine learning. But when we add quantum information or quantum algorithm, we can have three more combination. Classical data quantum algorithm, quantum data classical algorithm, quantum data quantum algorithm. So this is what three approaches. And then next one is quantum encoding. There are four encoding: basis encoding, angle encoding, amplitude encoding, hybrid encoding. So this is an important concept in any quantum computing, but for QML it is very, very important. Why? Because quantum algorithms are processing quantum information, but we have only classical information. So in that case, how can we take care of the data? Because classical data cannot be sent to quantum algorithm, because quantum algorithm is expecting complex number. Classical data are binary number. So one thing what we can do, we can convert the, or we can encode your binary data into a corresponding vector, meaning that if there are 8 bits in your classical information, you need 8 element vector. So the number of qubit, each element is 1 qubit. So if you have 10 bit of information, you need 10 qubit. That is what basis encoding. And angle encoding, you are using your data as the phase of qubit. What is the phase of qubit? The phase of qubit can be between 0 radian to 2 pi radian. So 0 to 2 pi. You remember this, right? Or 0 degree to 360 degree. So now you may wonder how it can be done. So the rotational gate RY, RZ, RX, RZ, RX, but RZ mostly we won't use. We will use RY or RX gate with the radian as the parameter. So how can we get the radian? For example, if your data point, for example, assume that your iris data set, sepal length, sepal width. So iris data set, sepal width having value ranging from 4.2 to 7.8. Assume that this is just a hypothetical number, not exact number. So you have to apply the normalization between 0 to 2 pi. So the mathematical normalization, we know, right, how we are normalizing uh, 0 to 1. Like that, we can normalize between 0 radian to 2 pi radian. Then that number will be passed to ROA rotation. That will encode your classical data into quantum data. Is this clear? The next one is amplitude encoding. What you can do, you can encode your classical data as the amplitude, probability amplitude. We know, right? Uh, alpha 0 ket, sorry, alpha 0 ket plus beta 1 ket. And here alpha and beta are probability amplitude, provided alpha square plus beta square equal to 1. Correct? You remember this fundamental rules of quantum information. So here the alpha and beta, if you have 10 qubit, you will have alpha 1 to alpha 1024, because 2 power 10 equal to 1024. So you have 1024 probability amplitudes. So what you can do, using 10 qubit, you have the possibility of storing 1024 probability amplitudes. So if your data, your volume of data is 1024, you will need n qubit. So that is the advantage of amplitude encoding. So, but what is the value? This is okay, but what is the value? That value is between 0 to 1. So now you know, if you have number, any number can be normalized between 0 to 1, and that will be positive to one of these 1024 value. That is how the probability amplitude is working, and this pi will have your classical data normalized between 0 to 1. Is it clear? This is for amplitude encoding. Hybrid encoding is using this concept, what is called, oh my god, there is a entropy. Yeah, the entropy concept. This is rho equal to, we know, right, the rho equal to, if I put lambda times outer product of x ket, and yeah, this is the outer product of x ket. So here the lambda is the amplitude, and this is the outer product of your qubit. So the hybrid encoding uses both amplitude as well as your phase, and by performing how I am telling phase, by performing the outer product, I am trying to utilize this quantum phase estimation concept, which allows me to utilize the phase estimation by this formula. Um, okay, e power iota theta, right? So here I will use this exponential form of my theta and iota, then the probability amplitude, all those things will get loaded with your classical data. These are the four encoding, and if you want to become a quantum computing professional, the encoding system, you should be very clear. And four, recently two more methods have been added. A good book is Maria Schultz book, where they covered the fundamental concepts of quantum encoding. and the other one is Mike and Ike book. That book also covers this encoding very clearly. So first read the Mike and Ike book, then move to Maria Schultz book. You will get the clear picture. And this is a summary of these four models I created myself by based on my understanding, and then asking various, collecting various books, and uh, organized using chat gpt. But it is, I tested everything. I just simply not copied the chat gpt thing. Then comes quantum information. The page is taken from Maria Schultz book. And now, to understand quantum machine learning, we should be very clear about the VQC and the PQC concept. So VQC is variation of quantum circuit. PQC is parameterized quantum circuit. So VQC will always use a quantum. This is PQC actually. This portion is the PQC. The overall setup is VQC. The overall architecture is VQC, right? So VQC uses hybrid. You can have a mental picture whenever you are in the context of quantum. If you come across the word variational, that is the hybrid, quantum and classical. So the classical system will see, you see the measurement. This measurement will result in the classical data. That classical data is analyzed by an optimizer here. Inside this one there is an optimizer, and then cost function analysis, all those things. That optimizer compare the output of this quantum computation with the previous iteration. Then based on the cost or loss, it will change the it will tweak the parameter. That's what we calling the optimization. Usually it is will be theta, meaning that usually the theta will be passed to this PQC. The PQC, for example, RY, if it is RY gate, that will use this theta. So each iteration, this theta will be passed to the parameter to the rotational gate. Then the same circuit will be repeated. Obviously, since there is a different parameter, that will give different result. So this will continue till we are getting convergence. This is what the high level architecture of any variation of quantum circuit. Then comes these are the advantages of the Saral theory. I'm not going to spend time. And the same concept I'm explaining with theta. Remember, I told that theta I, that's what this one. And very importantly, I want to cover this concept. So if you take quantum support vector machine, so let us take, this is your iris dataset. I believe all of you remember what is iris dataset. If you don't know, ask the question in Q&A, I will answer. So this iris dataset with the sepal length, sepal width, petal width, it will be passed to this quantum circuit. Petal width and petal length. There are four. Then it will return the output is the species. Species may be three species: 0, 1, 2. Species Setosa, versicolor, virginica. These are the outcome is be, it is a three model: 0, 1, 2. Oh my god. And return. Okay, right. So this is the output of this one. And here, based on, there are 150 subjects, so we will pass 150 rows to the pre-processing. That will be passed to this feature map. So there will be a feature map of 150 data that is passed to a kernel. That kernel will help us to classify your iris flower set. Then based on that, it will give 0 or 1 or 2, any one of the classes. That is what the quantum support vector machine for iris dataset. Now you may wonder how a classical system is being processed or classified in the quantum. all of you remember this one, right? In the classical system, we are two-dimensional, and in the see, if it is in the original space, we cannot classify because it is a non-linear. But after the feature map, it will become a linear kind of thing. Even this also will be helpful for you. This is what the higher elevation we are able to linearly separate. The linear separation is very important to build a computation. If any solution cannot solved by linear approach, it is not possible to use computing devices. That's the reason why we are finding a way to whether how can we linearly separate. That's why we are building a kernel which will elevate your data point, then we will linearly supply. But how it is done in the quantum? In quantum, one advantage is that it is a non-Euclidean space. See here, these are all Euclidean space. That is the reason why um, they need higher elevation to linearly separate. But in quantum, it is the Hilbert space where the values are mapped into a feature map concept is a non-Euclidean space. In a non-Euclidean space, even if you put a linear line or linear approach, internally it will be mapped to a non-linear approach. Hope you can recall what is the foundation of non-Euclidean space. Correct? That is why even though I am drawing a linear line between 0 to 2 pi, that will form a non-linear classifier like this. A non-linear separable or non-linear, I can't say it is a hyperplan, but a non-linear separation is possible. So this is the concept, and then this concept is extended to all quantum machine learning approaches. Of course, there will be little bit mathematical changes in those models, but fundamentally this is the concept. So here I would like to stop the theoretical or PPT based discussion. Now we will move on to the um, what is called our Q&A based discussion.